Well, it's a pleasure to have this meeting of the IBSAR and the SSAWA branch. We've had arranged a talk from Smaila Sanni, who is a new member, I think, of the IBSAR. Smaila works with Saggy West, which is a research grain sort of institute. So Smaila is going to talk to us today. So I'll let him introduce the topic. It's about bushfires, which is well known to the Australian landscape. Smaila, you're welcome to begin.
Okay, thank you very much. Yeah. Hi, everyone. I'm Smaila Sanni, research associate at Saggy West Cotton University. Today, I will be talking on modeling the rate of spread of fire using stochastic differential equation. Here, we are interested in understanding how fire evolved through time. So the question is, why are we interested in fire? Why do we want to study fire? Why are fire an important thing to model? Fire can have devastating impact to the landscape, to natural and urban landscape, and fire can disturb the natural ecosystem, killing wildlife and taking extended period of time to recover. In the urban landscape, fire can be deadly and can cause severe loss of property and businesses. These are some of the impacts or devastating effect of fire. Fire have much more better chance to be controlled and contained when they are dealt with at their source point. And this is the area that is of interest to this talk. Understanding a problem is key to solving it. In this talk, we are interested in the probability that a fire spread dies out before reaching an outbreak within the first 5 minutes. This talk has been outlined as follows. We'll look at the motivation and the purpose of the study, the fire data which are generated from fire experiment. We'll describe the accelerated phase of fire spread using classical approach and stochastic approach. The classical approach is the deterministic model. And we are going to examine some of the applications of the stochastic model in biological research and some application in agricultural research. And we'll make conclusion regarding the findings of the study. One of the purposes of the study is to understand the dynamics of fire rate of spread. What then is this fire rate of spread? Fire rate of spread is the rate at which fire expands. And this rate is measured by the distance traveled by the outer fire per minutes. We determine an appropriate fire experiment from which the fire data is generated. We understand the data by using some visualization and descriptive statistics and conduct statistical analysis by fitting a statistical model to the data and make conclusions and recommendations regarding fire containment. Developing a mathematical framework to study the evolution of fire through time, we made some simplifying assumptions. We assume that all fire starts small, some grow larger, and as they grow, their rate of spread increases to a quasi-steady state. To see this behavior, we look at 5 fire experiments and give a scatter plot of the experiment. The x-axis is the head fire rate of spread measured meter per minute, and the x-axis is the time, the elapsed time since ignition of the fire, and we can see that from the point source, the fire accelerates until it attains some sort of stability around this area. This kind of informed us on the mathematical formulation to use in modeling the fire rate of spread. But before that, we look at some literatures to see what has been done in this area. We saw that vast amount of literatures focuses on modeling the quasi-equilibrium rate of spread, and limited work is done on the accelerated phase, which is the phase before the first 5 minutes of spread. So the scope of this study focuses on the acceleration of fire rate of spread from the point source to the equilibrium spread within the first 5 minutes. In modeling the accelerated phase of fire spread, there are several factors that are of importance. They are the wind speed and the direction, the fuel type, moisture content, and these factors increases the variability in the fire rate of spread, and these needed to be incorporated into the model. The present model that has analyzed fire rate of spread or solved the problem include using linear regression. And this linear regression lacks some sort of flexibility because they give separate estimate for different conditions. And we understand that the rate of spread of fire exhibits some form of heterogeneous variance. The stochastic approach used in the literature involved the assemble approach. But the problem with the assemble approach is that once the parameters of the model are fixed, the model behaves deterministically. So, as we've seen in the experiment, each realization or runs has some inherent uncertainty associated with it. So, the fundamental question is that, can we describe the uncertainty associated with the rate of spread of fire? We'll look at how this problem has been handled using some deterministic model. Here is the classical model used. Model 1 and 2 are exponential type model, and model 3 is the Weibull model. The specification for this model as follows. R of T is the rate of spread of fire at time T. R of E is the rate of spread, the equilibrium rate of spread of fire. A is the rate at which the equilibrium rate of spread is attained. Alpha and beta are the parameters of the Weibull distribution, which is model 3, and these parameters are to be determined by fitting. For the exponential type models, which are model 1 and 2, the rate of spread attains the equilibrium rate as T tends to infinity. But for the power model, which is model 3, the equilibrium rate of spread is never attained. we look at a fourth model, which is the logistic function or the S-curve, and the goal is to estimate these parameters using a weighted least square regression approach. Here are the methodology for the fit. We use the Lavenberg-Marquardt method together with the bi-square weights, which minimizes the weighted sum of square. The LM method switches between the gradient method and the Newton-Gaussian method. The LM method acts like the gradient method when the parameters are far from the optimum, and acts like the Gaussian method when the parameters are close to the optimum. These methods are available in MATLAB. Here are the fits for the logistic function. These are the parameter estimates for the logistic function. We obtain the initial condition to be 0.2, and the equilibrium rate of spread, the estimate for the equilibrium rate of spread is 1.57, and we have this as 1.622. The root mean square error is 0.445, and the coefficient of determination is about 65%, and this implies that about 65% of the variability in the fire rate of spread is explained by the model. So we set up some confidence, 95% confidence band for the parameter estimate. And we also assess the quality of the fit through the residual plots. And here is the top panel, the standardized residual versus the fitted values. And we could see that the residual plot tends to fan out at this point, indicating or suggesting some sort of violation of the constant variance assumption. And we also look at the bottom panel, which is the raw residual versus the elapsed time since ignition, which gives some indication of increased variance with time. Here is the visualization of the four models. We have the head fire rate of spread, meter per minute, versus the elapsed time since ignition. And we could see that the S-curve, which is the blue line, the blue curve, captures most of the variability in the spread. This is the Weibull curve, and the two light red are shades of the two types of the exponential curve. Since the residual plot indicates some sort of increased variance, and we could see that the nonlinear regression could not adequately represent the rate of fire rate of spread, we use the stochastic differential equation approach. The stochastic differential equation is an equation of the form where the rate of spread is represented by a deterministic aspect and a random aspect. The essence or the goal of this stochastic differential equation is to find a stochastic process, which is the fire rate of spread, that satisfies this integral equation. We have assumed a Brownian or Wiener process here, a Brownian motion or Wiener process. Here is the stochastic differential equation version of the logistic function that we have used, we made some assumption by looking at the plot. We assumed multiplicative noise, which implies that the variance increase with increasing fire rate or spread as seen from the data. And if this parameter, which is the spread parameter, if this spread parameter is set to 0, the stochastic approach will reduce to the deterministic equation as used in the nonlinear regression. This is the initial condition. And to solve this problem, we employed the Euler-Maria iterative algorithm that discretize because we have a continuous state space stochastic problem. So the Euler-Maria algorithm discretize this problem and solve it in discrete space. So here is the simulation of the stochastic fire path. We did 10,000 realization of the stochastic fire path. The top panel represents the 10,000 stochastic simulation. We only represent the first 6 fire paths, which we have the mean along the y-axis and the elapsed time since ignition along the x-axis in minutes. The red parts are the stochastic fire path, while the blue solid curve is the average or the mean of the 10,000 stochastic fire path. See how the variance increases with time. We have this lower panel which plots the standard deviation of the spread along the y-axis and the elapsed time since ignition along the x-axis. And we could see that the standard deviation of the spread increases with time up to a point where it attains some sort of stability, which is quasi-stability. In simulating this problem, we estimate the spread parameter by requiring that the variance of the rate of spread takes the root mean square error when in equilibrium state. We also look at the distribution of the fire rate of spread from the stochastics, from the simulation. We take the different distribution of fire at different time points. We could see that for the top left panel, we look at the distribution of the fire spread at 1 minute. The top right panel, we look at the distribution of the fire spread at 2 minutes, and we look at the distribution of the fire spread at 3 minutes and at 4 minutes. We could see that the rate of spread, the distribution of the rate of spread at 1 minute is skewed, become less skewed at 2 minutes, and more symmetrical at 3, and becomes symmetrical at 4 minutes. So we also determine the probability of containment, which is like the quenching effect. We calculate the probability that the fire rate of spread will self-extinguish. Here are the probabilities at different values of sigma, and we obtain the estimate based on 10,000 realization. We did this computation by taking the equilibrium rate as the initial condition, and we could see that the probability that the fire will self-extinguish increases as this ratio decreases. To see how this behaves, we simulate this behavior. And this this plot here shows the simulation where the path self-extinguished. We have assumed that the fire begins at the point where it attains equilibrium, and we want to see if it self-extinguished. From here, we could see that one of the paths, which is the green path, self-extinguished. So now we see some application of stochastic differential equation to biological and agricultural research. In biological research, stochastic differential equation has been used in cellular dynamics, where some cells possess sensitivity to drug therapies and others exhibit resistance to it. Has also been used in animal genetics. In agricultural research, stochastic differential equation has found extensive application in modeling crop response to disease changes, to changes in growth factors and crop epidemic like crop disease spread. There are some relevant equations that describe cellular dynamics. We look at these two equations captures the two different situations regarding where the cell is sensitive to drug therapy and situation where the cell is resistant to drug therapy. We could see for the first equation, we could see that the evolution of the cell is represented by the growth phase, the transition, death, diffusion, and dissemination of the cell. For the resistance to the drug, the spread is represented by the growth, transition, diffusion, and dissemination. One thing to note here is that both have transition, but the signs are different. For the resistance, the drug, the transition assumes positive sign, while for sensitivity to the drug, it assumes negative sign. Here is another application of stochastic differential equation to modeling drug dynamics. The evolution of drug in the body is represented by the elimination compartment, delivery, and diffusion. The specification for this model, which is the D, is the drug concentration in the body. Then the D drug is the metabolic rate coefficient of patient, and the U of T is the rate of drug delivery. The cranial motion is assumed to introduce stochastic elements into the modeling process. Here is another relevant application of stochastic differential equation in agricultural research. Crop disease spread is a big problem in agricultural research or to farmers. And this equation represents crop disease spread generally. We could model the leaf or the gloom area disease spread using version with this equation, which kind of have similar structure as the rate of spread of fire, in that it has the growth phase and the diffusion phase. The specification of this model are I, which is the level of infection, B is the rate of transmission affected contact, I mass is the maximum number of potential affected individual. Then, another application of stochastic differential equation is in chicken growth, where the growth is represented, the change in growth is represented by this equation. We have the growth phase and the diffusion phase, and the initial condition is assumed to take some exponential function. And this equation is deduced from the Gumpert equation, which is likely applied in agricultural research to model growth. To conclude this talk with the stochastic differential equation allows us to generate statistics such as the mean, variance, containment probability, and distribution for fire rate or spread. For the first time, we have successfully used a stochastic differential equation to describe the fire rate or spread, providing useful statistics for fire management. The results indicate a narrower confidence band for the stochastic model compared to the nonlinear regression model. This gives some implication for fire management with regards to the different prediction bands from the different models. Thank you.